Excellent. Well, thanks again, everyone, for joining us today. We're very happy to discuss this project that we rolled out about a year ago, and it's focused on the MTO's travel time project, where they essentially deploy one of the largest travel time networks in North America. There's 223 sensors across Central region, and so this is not even the full of MTO. We're starting to look at expansions into the east, the west, and the north. So this could turn into an even larger one down the road. But yeah, thanks for joining us. I have long-term colleague Yeatland Wong from Transnomis joining us today to kind of speak to the software side of things, and that's really the bulk of it. So Yeatland, thanks for joining us today.
Thanks for having me.
Perfect. So we're just going to jump right into it. We're going to try to keep this. Well, I have an agenda slide, so why don't I say this when I'm on that slide? Going to try to keep this short and sweet, usually about 30 minutes of actual content, and then about 10 to 15 minutes for questions at the end. And I suspect we might get a lot of questions for this one. So if we do run out of time, we will follow up with written answers to all of those, so don't worry. And to that end, you'll see in the sidebar menu of the GoToWebinar panel that there's a question box. So please, as we go, as questions come up as we're speaking, please just throw the questions in there. We won't answer them till the end, but at least then we can kind of collect them while they're fresh in your mind. And so generally what we're going to do is going to provide just first general overview of the project. What was it? What do we do and why? Then I'm going to jump in, talk about the sensors. So we provide the sensors at Ramudden Digital, and then we partner with Transnomis for a very long time on providing kind of the software that drives the system using the data from our sensors. And so Yeatland's going to take over and kind of speak to the architecture, some of the challenges along implementation, and then the fun part of diving into the actual system to show you a live demo of what it looks like and what you can do. And finally, there is going to be a quiz question. We do this with all our webinars where we kind of pick out a little skill testing question. It's usually, a number or something that stands out. So keep your eyes open as we go through the webinar for what might be a question later on, and the winner will get a little gift bag sent to them with some swag in it. And just for clarification on that quiz question, within the question box within that menu, that's where you submit your answer. So it'll be an A, B, C, D multiple choice question, and so just the first one to put in the right answer. My colleague Samantha is watching here too, and she'll pick up that person, and then we'll get in contact to send you that. And then of course we'll finish it all off with a Q&A. So let's dive right into it. Of course my mouse isn't working now. Let's try the keyboard. Okay. So just what was this project? This is, again, I think the largest in Canada, potentially North America, but it was a design build contract that the MTO put out in 2022. And design build basically means that they give you kind of the output requirements of what they want the system to do, but are not as prescriptive on exactly how that's going to be done. And so we partnered with Black & McDonald and Transnomis and Lee Consulting to bid as a team on this project. And then we were successful and rolled it out throughout 2022 and 2023. And I think the system went live summer-ish of last year. So it's been running for quite some time now. And if you see the map here, each of those blue icons is a sensor. So we have 223 sensors across Central region. And the purpose of this system is to primarily generate travel time and average speed data between each of those points. Primarily to drive VMS messaging, those big electronic signs you see on the highway that tell you 22 minutes to get to 401, those annoying ones that have really large numbers sometimes. That's our sensors driving that, and ITS Central generating that data for the MTO and then passing it to them to post the messages to the signs. And there's also kind of a secondary use intended for this is to do congestion monitoring. And I don't think this has really been taken up full blown just yet, but I know it was part of the original vision for this system is to, instead of utilizing Sci-Fi radar or loop-based count stations to do all your congestion monitoring on the highway, to move to a dense network of travel time sensors to perform that function instead. And the rationale with that being that kind of count stations and loop data really just measure volume, occupancy, and speed at that one single point where the sensor is. It's like a slice in the roadway, and then another kilometer or 2 or 3 down the road, you'll have another sensor that shows you what's happening at that slice of the roadway. And the challenge has always been what's happening in between. And so the value in these travel time sensors, or Bluetooth Wi-Fi detectors as they're called sometimes, is that they rely on measuring what's in between the sensors, not what's at a single sensor. And I'll get into in a moment on how these sensors work, but essentially they're sniffing anonymously for Bluetooth and Wi-Fi devices that are within a 200-meter radius of each sensor. And so it picks up a unique ID that it registers at one sensor, but that on its own is kind of useless. It only becomes useful data when it passes by a second sensor. And so when you pass by the second sensor, it knows that unique ID has gone from point A to point B, and it's taken X amount of time, and it's this far apart. So you can do a rough, simple calculation on the average speed between those 2 points. And so now with these sensors, you actually have full coverage of all these roadways, such that you can generate your own congestion heat map and kind of a color graded map, much like Google creates. And Yeatland will show you that in a little bit when he pulls up the platform. But that was the vision for it, is to kind of scale back some of those non-intrusive count stations that the MTO has all over the 400 series highway, and kind of blend it in with this travel time Bluetooth Wi-Fi detectors. So that's the gist of it. You'll see the pictures here. I'll get into a bit more about what these are, but these are what our sensors look like deployed in the configurations prescribed by the MTO. But let me keep going here. So as I mentioned, this is an MTO project. Black & McDonald was the lead electrical contractor on this, and then subcontracted with us for the hardware, Transnomis for the software, and Lee Consulting for the design. Again, the geographical boundaries of it is essentially central region. If you're not familiar with that, it goes all the way down to Fort Erie, Niagara area, as far north as Aurelia, and then kind of out to Bowmanville and Cambridge, Kitchener on kind of the western side. And you'll notice as we move out to the west, there's not quite the sensor density that we'd expect. So we're hoping to fill this in a little bit, but certainly within the GTA core, we have a very dense deployment, which is great. And one thing to kind of highlight is, I've said it a few times, but just how big this project is. And maybe for some large consulting firms, this is not too crazy, but this is by far the largest project that we've ever deployed our sensors on and that we've been involved with. And the same is true for Transnomis. So we've been working together for almost 10 years, actually maybe right about 10 years last month, on collaborating with the sensor. So we make the sensor hardware, they develop the firmware that runs on there, as well as the software that receives it. So we've been working on this for a very long time. So we have 223 sensors, and what this really means is just a ton of data. So we have 38,000 detections coming in every minute, and processing that, in the cloud with their services is not an easy thing per se. And we're also matching, those devices are matching 48,000 times per minute as well. And this is 600 kilometers of highway, 82 plus travel time paths, skirting throughout the GTA there, and then driving messages to 137 signs. So this is a very cool project, but kind of ran into some scale issues where, and we'll talk to it in a few slides of just how do you process and manage all this data? How do you manage, intermittent sensor outages and things like that, self-healing paths and things like that. So big project, very exciting, and went much more smooth than we maybe expected. And so very pleased with the outcome. And I think MTO is as well. So as I mentioned, we are the manufacturer of the travel time sensors. We call it the ACE, the AIS. It used to be the Stinson ACE, now it's the Ramudden ACE. And it's a fairly straightforward device. It's just scanning for Bluetooth and Wi-Fi MAC addresses. And so we support both Bluetooth and Bluetooth low energy, and of course Wi-Fi as well. And the low energy one has been very powerful for us to kind of capture a lot of those accessory devices that now use Bluetooth. So we have a very high capture rate, and even with Bluetooth max scrambling and things like that, we've still maintained quite a strong detection penetration rate. So some of the differentiating features of our sensor, one of the most important is its open protocol. If you have any familiarity with travel time systems, when I designed the sensor, my intent was to really follow that traffic NTCIP mentality where there's interoperability between sensors. And often the existing market, when we first entered 10 years ago, was everyone sells you the hardware and the software as a piece. And they're not open, they're all proprietary, and you can never mix and match another software or another piece of hardware in that. So you're kind of locked in with that vendor forever. And that's still the case. As far as I know, we're the only sensor manufacturer that offers this open protocol. And currently we're integrated into the Transnomis IT Essential platform, as well as the Genetec Security Center platform. So we find in Ontario, almost all Transnomis users, and then in Quebec, all Genetec users. So we love the fact that we're cross compatible and we could be integrated into any platform. There's just only a few kind of open-minded software vendors that are willing to do this kind of integration, and those so far have been Transnomis and Genetec. So just quickly touch on some other features. We have an onboard web server. So much like you access your Wi-Fi router at home to change settings, same thing here. You can either remotely or locally jump on there and you have access to all the menus, all the diagnostic configurations. So it's super simple. We've been building these since 2015. We still do in the back here right behind me. Forgot to mention our cameras seem to not be working today for some reason. We can't figure out why, but otherwise I'd be showing you this is where it's made here in Woodbridge, Toronto area. And again, Transnomis designed the firmware for us and continuing to update that. Our detection range for this outdoor unit with these dipole antennas is about 200 meters. It's actually even more than that, 250, something like that. It depends on the conditions. And then we can vary the antenna types for urban arterial deployment so that it's a more reduced 100 to 150 meter range, depending on what you want. And now our big value add to this sensor is our electronics and kind of system integration knowledge. So we have the ability to kind of adapt to any power source, any communications method, and mounting options, things like that. So we can support AC power, DC power, power over Ethernet, and now our most popular focus is street light pole tap. So tying into that NEMA socket in North America. That's just an easy way, 2 banding straps and plug this in and your node is online. And the reason for that is, much like this contract, we began integrating LTE modems into every single unit so that we can have everything pre-configured and just start pouring data to the cloud the moment it's turned on. And we support things like network time protocol, time sync, remote firmware updates, and all those standard features you'd expect from a professional device. And even part of this contract, we had to go through NEMA TS2 environmental testing. So went through all the kind of the on-off cold starts, and the full, minus 34 to plus 74 temperature range. So very pleased with how this turned out and excited to kind of keep running with the momentum we have. Now, as far as the form factor that we used for the MTO project here, there's 2 variations. There's really 3, but most of those other 2 are very similar to the one on the right. And so what differentiates the 2 is primarily the power source. So these were designed to be completely isolated from the MTO's infrastructure and their network. And in that, it means basically their control cabinets. So they really didn't want to put anything else in the control cabinets. They don't want to share keys for the cabinets with third-party contractors. So they wanted everything to be external. And so what we have from the cabinet is purely just an AC power connection. So you'll see we use Unistrut to kind of mount on the exterior of the cabinet. And then that AC power goes to this disconnect box. And this is essentially just a breaker, but it allows a contractor to access the site, cycle power, investigate does power exist or not, to be able to perform maintenance on the sensor. So if there's something wrong or needs to be replaced, they can kill power locally without touching the main box and do what they need to do. So this is the structure on 194 of the sites, which are AC powered. And then there's a few sites where they just didn't have any infrastructure and we needed a full solar system. And so we've been designing and building solar systems since our inception 10 years ago. And so we supplied the solar system as well as the sensor. In this case, there's no concern around box access because this is a dedicated enclosure for what we're doing. And so the disconnect in this case would be inside this metal battery box and enclosure. And there are 29 of these solar sensors. And one thing you might notice, the solar panel, if you know how much power these sensors typically consume, on the order of 3 to 5 watts, it might look really oversized, and you'd be right in that assessment. So we always oversize and over-engineer our solar systems because it can be challenging. If they're not maintained and cleaned in the winter, then they won't work as designed. So we always upsize our panels and our batteries, and we certainly did that in this case because the contract includes maintenance throughout that whole 5+2 year period. And so these things have probably 3 times the solar power it needs to actually run year to year. But that should, as the battery degrades or in the winter, if the snow panel is covered in snow or partially covered or dirty or dusty, it's still going to generate more than enough power to keep it going. And so that's it for the sensors. Again, if you have any questions as I'm speaking about that, throw them in the chat now and we'll get to them later. But I'm going to start handing off now to Yeatland to talk about the architecture and the software in a bit more detail.
Thank you. Thanks, Michael. Yeah, there's not much. I'm not going to go into too much detail on the system architecture. We're essentially pulling in the data from the sensors. They're being transmitted via LTE modem cellular data into the ITS Central software. And from there, we're pulling in that data, calculating the travel times within our system, matching them up between multiple sensors, and then we're outputting that over to the MTO travel time system via a REST API. So MTO's system is what takes in the travel time messages, and they're going to be posting it directly onto the VMS site, VMS signs themselves. We can also pull in data from their MTO partner agencies in order to do further messaging, especially when we're talking about signs that are interregional or perhaps where the roadway crosses a region. You as a driver don't really care that there's a boundary between multiple regions for the MTO's partner agencies. So of course you're going to appreciate that message either way. I will also mention that this project is, I've been doing travel time systems since around 2008. I think I did my very first travel time system for City of Calgary, 2008. We used with a competitor to Ramudden at that time, and it was maybe only about 12 sensors or so, 14 sensors. But it's really interesting to see how this has changed and how this scales up. And I'll talk about that a little bit later as we go on. So, your basics over here is within the system. We're of course pulling in those MAC addresses, sniffing them out, and then doing retrievals. And this is, this is one of those things I was talking about, the difference, just the sheer scale. Number one, 2008, not everybody had a Bluetooth device on them as they're driving by. Back then, it was about 4%, 6% of vehicles had some sort of Bluetooth device, and that has really scaled up a lot. So we're getting a heck of a lot more matches as those vehicles are passing by. We're using only the matches from the last 20 minutes. We're removing, of course, outliers. If you've got vehicles that are traveling way too fast or way too slow, I'm sure you've seen both of those types of vehicles on your daily drives out there in Ontario. So we remove those outliers because we're trying to give a travel time that reflects the experience of the vast majority of our drivers. We're biasing as well the samples towards the newest samples. So although we're looking at matches from the last 20 minutes, we're wanting to bias towards the earliest, the latest matches, not the earliest matches. And there's other sorts of adjustment factors that are applied that might be unique to the different paths that we're working with. This kind of gives you a quick look. So, the travel times throughout the day, of course, are changing, and you can see there's those high travel times during peak hours, exactly as you expect. And but still, we're getting plenty of matches at 3, 4 o'clock in the morning. One of the challenges is that the signs need to be bilingual. So you can see here the sign messages we've got are capable of doing graphical messages updates. These are not being posted quite yet to the system. So the system is ready, but it hasn't been launched. You're going to be seeing this fairly shortly. But yeah, these new messages are essentially bilingual. They're agnostic of English or French. Technical challenges. So again, as I mentioned, I've been doing this for a long time with these travel time systems, but the sheer scale, like scaling up, there's a huge amount of volume of data, and even before then, I mean, let me give you an example. You've got 12 sensors, and say you're mucking around with them, you make a configuration problem change, and like, oh, oops, I configured this incorrectly. Well, let's just change those 12 sensors. That's going to take me whatever 10 minutes. But when you're working with hundreds of sensors, any change or any error you make as the configurator or the engineer or even as the integrator, you're multiplying that by a huge number. And so we had to do a lot of automation in order to address some of that in a more timely manner. The volume of data coming in, there's just a huge ton of data coming in, and I think I was quite surprised at that. My technical folks in the background, they were able to handle that. They were able to deal with that, applying, again, because we're doing a cloud-based system in this case, they were able to increase the amount of memory or apply improved algorithms, etc., in order to deal with the sheer volume of data and to get the latency down on the calculation times. Sensors. So sensors. There's other issues with sensors, and this, when I say going on or offline, we're not talking about the quality of the sensor itself, but rather when you've got hundreds and hundreds of sensors out there, the chances that some contractor somewhere along the system is going to, say, shut down power to something, or you have a flicker on the power grid, or perhaps you've got an area where there's no traffic, whatever it is. Again, if you've only got a few sensors, you might not see that at any given moment. When you have 223 sensors out there at any given moment, there's always a sensor that's offline somewhere along the grid, or is insufficient data to do a match. Consistency of travel times. You've got other challenges, such as whether or not those whether or not the travel time is homogeneous along your route. You've got other issues, such as if you've got matches, people are taking alternate routes, they're still going past your sensors, and of course our algorithms are trying to sort that all out and figure out what is valid data, what isn't. Maybe I'll pass this environmental challenges bullet over to you, Michael.
Yeah, absolutely. And this is an interesting one, because it's kind of, I'm sure a lot of you have seen MTO contracts and MTO drawings, and one thing that doesn't come through our drawings is kind of topology, and the actual kind of elevation of the roadway or the grounds that you're looking at. So it was very interesting to kind of do our site surveys, and then also to kind of implement the solution. So when we deploy these sensors, we have kind of an ideal positioning for them, and it's usually 10, 12 feet off the roadway, with a limited setback from the edge and not too much ideally. And then trying to match that with where the cabinets are located, because MTO obviously, and rightly so, was trying to utilize existing infrastructure. So we were kind of tied to where they put those cabinets in. And I remember in the bid process, we looked at them all, and there was a few kind of sites that we weren't 100% on, but everything looked generally okay. But then when it went to actual install, we did a detailed site survey of every location, and it was kind of funny because even though some sites would look like they're 20 feet off the road, and they would be, but they'd be 100 meters in the air on a hill, and so it's not quite ideal conditions to be able to detect. And so we ran into a couple like kind of dimensional, positional issues with, where, what size pole do we want to install? And often what we found was when we say 10 to 12 feet off the roadway, we mean from the roadway surface, not from the ground where the cabinet is installed. And often it's in a ditch or down with a gradient difference. And so we'd often have to go back and say, no, let's focus on measuring from the roadway up. And so sometimes we put a 20, 30 foot telespar that's used at the cabinet. Sometimes it would be a standard 10 foot. So it was just getting through those positional and like kind of sensor placement issues more than anything else. And obviously when we have kind of distances from the roadway or obstructions, if we're right next to a bridge, we obviously, these signals are very much line of sight focused. And so we have right next to a bridge, we're not going to get good detection in that direction. And so just trying to accommodate that, understand the limitations, and then compensate for that in the software was a bit interesting. But generally, that probably affected 10 or 15 sites out of the 200 plus. So it wasn't too bad, but certainly something to keep in mind if anyone here is looking to plan a future system.
Accuracy comparison. So there's some interesting challenges to, you ultimately you want to calibrate your system. You want to make sure that your system is working well and the travel times that you're reporting are reasonable and accurate. And so we did a couple of things. We did a floating car methodology of checking that our system was accurate. We also collected Google travel time data and used that to compare to our data. The Google travel time was excellent for being able to capture the entire system all at once. Our floating cars, we spent hours driving through the system during peak hour, during off-peak hour, in order to test and calibrate. It's good to have 3 different measures, because this way you can say, well, if 2 of them agree, we can figure out which one is the one that's not working. And believe it or not, there's the Google travel time is not always the best of those 3. It's often assumed that that's going to be the be all and end all of what is accurate, but surprisingly, it's not. In terms
sorry,
of
on that piece, I wonder, because that's always the challenge when we talk to people about these travel time sensors, is they wonder, well, why are you going to deploy your own hardware when Google and all these guys have so much data out there? Is that like inevitably, I think it will surpass us. And at some point, 10, 20 years in the future, the data will be so good, especially with connected vehicles, that none of these sensors would be necessary. But certainly in the meantime, what we keep hearing and what we heard from the MTO is part of the rationale of going this direction is that the data quality from Google is 1, very expensive, but 2, still lacks in accuracy. And I wonder if you can speak to that slightly, if that's what, it sounds like that's what you found, but I wonder if you have any other anecdotes or kind of comments on kind of the comparison between what we're getting from our sensors compared to what Google's providing.
Yeah, I would say, especially speaking as a former municipal engineer, and so I approach a lot of these projects from that perspective. By the way, I'm thinking about the cost benefit, I'm thinking about the accuracy. So I would say, to answer your question, the biggest thing in my Google comparison was the cost. It would surprise you the sheer amount of money it costs to do a week's worth of comparison. I won't get into the numbers, but I will tell you, as a taxpayer, as a municipal engineer, if we had gone for Google travel time, instead of this entire sensor system, there's I won't get into the specific numbers, but it easily pays for itself to not go with paying Google for those travel times. From the accuracy, yeah, there are certain areas where it is perfectly valid, right? Google travel time could have easily replaced the sensors, at least from an accuracy point of view. Where it falls down is where there's lower traffic, and I would say that the system is starting to do a lot more guesswork as opposed to using actual data. Let's moving on to expressways versus collectors. So this is one of the fundamental issues when you're looking at something like the Ontario 401 expressway. There are expressways and collectors, they're parallel routes, and a travel time sensor is not going to be able to differentiate between a vehicle that's traveling on the expressway versus the collector. But because they are completely separated roadways running in parallel, your experience is going to be completely different between the two of them. So that is one of the huge challenges here, and it's not something that can be resolved easily from a technical way. I've never found a way to be able to differentiate between the roadway, between the expressway and collector, using purely from data. The kind of the way that we're really dealing with that ultimately is kind of being able to post a message. And I think that and it hasn't launched yet, but being able to post a message where the two routes are pretty much the same. However, when you have a major collision or something like that that's going to affect one of the two routes, then being able to post something else that says, instead of saying, hey, this is going to take you this much time, but rather say, hey, the most important information is the expressway has a major delay on there, take the collector. Other issues, challenges, ultimately, if you have more, has always been an issue with all travel time systems, is as you get more congestion, you get less samples. As you have less samples, you're going to have poorer accuracy, poorer quality of data, and that's just inherent to a travel time system. And so that's something that having the right density of sensors makes a huge difference. All right, let's if you can pass over.
Sorry, I was just looking at the time and realizing that we're coming a little close, so maybe let's do a short and sweet 5-minute demo, and then we'll jump into questions if that works for you.
Sounds good. Sounds good. I got the hint.
Good.
Here we go. All right. Live demo here. This is the part that you're interested in. So here's the system.
I'm not seeing
all
it
of those
yet.
little. Oh, all right. Let me know if you're receiving this.
Nope. Sam, can you see it?
Yeah, I can see it.
Okay.
Okay, go for it then.
All right. So yeah, you can see every one of these little blue dots. That is one of the sensors. What we've done here is we've created a digital twin to each of the dynamic signs that are out there. So we've added in I apologize. Sorry, give me a second. I just got locked out of my system from our security. From my security.
It's very secure. That's why.
It's very secure. My VPN just said, you know what? It's going to take this exact moment to lock me out of the system. I'm going to jump over here to the some of the dashboards as well. We've got dashboards that can provide a look at major delays that are happening, where they're happening throughout the system. Here's a visual representation. This dashboard over here allows me able to see, you can see right here, we've got some hotspots along the 401, surprise, surprise. It gives you a wonderful, quick bird's eye view of this system. I can take a look at my sensors, the uptime for the sensors, as well, getting into the data over here, being able to look along those travel time paths and see what's happening live throughout the system. And let's see if this is back up and running. Nope. All right, let's go back to our slides.
So Yates, if you want, I can jump in and kind of show some of the OD stuff if you want to try to get that working.
Yeah, that'd be great. Thank you.
Okay, let me just take back control. I can now see your screen, which is good. And I'll show my screen. So just to speak to general capabilities, often these sensors are used for travel time purposes. But one of the key things or kind of functions that it can also do is origin destination. And for whatever reason, I've not seen this utilized, certainly not used by the MTO just yet, but they have all the data there. But generally, it's not used as widely in North America as we see in Europe. But because we're tracking a unique ID throughout the system, it's much like, so these systems are not used in Europe very much. They are very big onto number plate or license plate reading. But this is something similar where it's capturing a unique ID, it's anonymizing it at the edge and then sending it to the cloud. But at least for that one day, as you travel through the system, you're a unique ID that can kind of be picked up at each sensor station. So when you have a dense network of sensors like this, you can actually watch the route that someone takes as it travels from one sensor to another. And a single route is not so interesting, but when you look at scale, you can start to see kind of how people travel through your network. Like, is it mostly commuter traffic up to 400 coming down during the day? Or are they coming mostly from the east or the west, or what percentage? Or if you look at certain neighborhoods, you know, in Yorkdale area, you know, where are commuters coming from? And you can start to see trends about, you know, where people come from, where they go. I know within arterial environments, you know, more municipal areas, we're often looking at major events like the hockey game or, you know, arenas and things like that, or concerts, to see kind of how do people, you know, enter the city and get to the venue, and also how do they exit? And then by understanding those patterns, you can start to adjust your signal timing, your messaging, and kind of your preparations to kind of accommodate those heavy routes that people are taking. So just an FYI that these types of sensors are very well suited to generate that type of data. And so that's a secondary use. It's not just travel time and average speed.
And Michael, I'm now back up and running again. Just logged into my VPN. Would love to show the last little bits here of the system.
Perfect. So just folks, just so you know, we will stay the full hour probably just to answer questions, but I understand you guys have other things to do. So we will send out a recording after, so that you can always watch the questions later if you have to run.
Just want to confirm you're seeing my screen again now?
Yes.
Okay, so I was mentioning that we also created a digital twin for each of the VMS signs. So you can see over here, each of these signs along the Ontario system. I don't have direct access to those signs, as I showed you in the architecture. So I create the digital twin. I have the sign location, but it also has the size of the sign. And here I can show you what I'm intending to post, and this becomes a bit of a mock-up of what those signs should be looking like on my end before I pass it over to the MTO system. Here's that, quick little previews of all of that. And ultimately, if you click on anything, it's an intuitive system. Here's a travel time path between the sign to the airport, for example. You click on something, it gives you quick information on that. Average speed, 55 kilometers per hour. You know, travel time, 27 minutes. Click on more information, and I'm going to be able to get a lot more information on that particular travel time path, get into my diagnostics. I can compare between paths, do a lot of my analytics from there. That's about it from the live demo part, and we can go back to those slides now.
Perfect. Short and sweet. I like it because we are pretty short on time. So that's it, guys. Thanks you so much. I saw a bunch of questions coming in, so we're happy to kind of move over to that now. Oh, no, we forgot the quiz question. Okay, so this is the exciting part. So I'm going to put up the question now, and then I will show the answers in a moment. Again, multiple choice question, put your A, B, C, or D answer into the question box. First one to answer the question correctly will get the prize, and your potential answers are as follows. So how many Ramudden ACE travel time sensors were used in this project? A, 220, B, 223, C, 225, or D, 228? Sam will let us know when we have a winner.
We had a winner almost instantly. Some people were definitely, actually we have a lot of people who answered correctly, so a lot of people have been paying attention. The first person, however, was Romaine. So I will reach out to you afterwards to get your shipping address.
Perfect. Congrats, Romaine. Glad to see you joined us here. Okay, so now to the fun part is questions. So Sam, if you want to just run through them, and then Yates or I will take them. I think I'll take hardware related, and Yates will take kind of system related.
Okay, so there is quite a few questions. So I'm just going to start from the oldest. Someone asked, what is the DC power requirements? What is the setup time for a portable temporary setup?
So then the DC question, DC input is 9 to 32 volts DC. We can also, and that can be supported through passive PoE, or we also have the option to support true 802.3 PoE, which is like a 5648 volt input. So either straight DC 9 to 32 volts, or your traditional kind of PoE switch or injector would work as well. And then as far as the temporary setup, what you're seeing here is our ideal temporary setup, where we have our all-in-one. This is our version 3 of the unit, built-in cell modem with a light pole tap. With this, you can install in about 5 minutes. It takes you longer to set up the lane closure than it does to put the sensor up. If you're talking in a VMS, we usually use our shelf mount sensor and install with a puck mounted antenna. That one will take more like half an hour to install, and then about 10-15 minutes in the portal to add the sensor details, draw the path, and things like that.
And I just wanted to note that we are at the end of the scheduled time. We're going to keep answering questions, but if anyone needs to jump off, we are recording this, and we will be sending everyone a recording tomorrow in case you don't get these last couple questions. The next question is, what is the percentage of vehicles captured? Are there geographical differences?
Geographical, certainly, if that's like country to country, I have no idea, to be honest. We've only done deployments in North America, really. But our capture rate varies depending on conditions, but it's typically between 30 and 50% of vehicles. There's some sort of device in someone's pocket or in their vehicle, and quite often multiple. But we certainly don't capture, like every single vehicle has Bluetooth or somebody with a smartphone, but we don't capture every single vehicle or device. This is not intended to be used for volume calculations. This is purely trend information, but we capture statistically enough of the devices that you can extrapolate very accurately the conditions on the roadway.
Do you calculate delay for each segment or a route? If so, then how do you estimate or calculate free flow travel time? What are typical sample sizes of detected MAC addresses out of total vehicles traveled of a segment?
Okay, so for the second one, we just answered that, but for the first one, I'll give my 2 cents answer if you want to add anything to it. We typically, delay is typically something that's calculated on a per sensor basis. So within our protocol, we capture when we first see the device, and then how long it sits within our detection zone, and then when it departs our detection zone. And so kind of the entry time within the zone, and then its exit time. And so with that, we can kind of capture time within the 200-meter detection range This is not really used on highways so much, more for intersections. So you can get a rough estimate of intersection delay for vehicles.
I'll add to that. So there's part of the algorithm where I'm trying to recall the exact part, but I can't remember the numbers we used. But there's certainly a percentile where we know that the typical undelayed travel between point A to point B is 27.3 minutes, etc. And then we have a percentage of that if the vehicle is delayed by more than X percentage, then we call that a minor delay, and then there's a major delay and a critical delay. And so that's how we categorize it and indicate on our map, are things good, not so good, or really terrible?
Yes, I misunderstood the word delay there. I'm thinking traffic signal use, but no, that's very fair. And just to add to that, it's free flow is typically at nighttime. That's when we'll see free flow conditions. So just like you saw the graph earlier, in the nighttime hours, we kind of see what no traffic looks like. That typically gives us our baseline. And then we can rate the daytime performance accordingly.
Yeah. Someone asked, how does the system adopt to an urban environment? For example, differentiating between drivers versus Bluetooth from transit riders, cyclists, etc.
No, maybe I'll give it 2 cents, and you might have an opinion there, Gates, as well. So this gets more challenging when you're in an urban environment, but we're starting to see quite a large deployment. We've got 60 of these in Durham, we've got some in Toronto, I think we got 45 or so in Montreal. And so we're starting to see a lot of interest in kind of urban deployments, typically at intersections, because you capture the most kind of cross traffic there. And the main use case is to just generate those congestion maps and notice in a minute by minute basis when slowdowns occur. And there is challenges with differentiating between different modes, especially when you have completely stopped traffic. And it ends up getting a little bit sophisticated with cluster analysis, kind of comparing, because typically vehicles will all travel a similar pace, walking people will walk at about the same pace, and cyclists as well. And so it's trying to differentiate those clusters of matches and identifying, is this a vehicle, pedestrian, or bike? But yeah, it's a little sophisticated there. I don't know if you have anything to say to that, but
yeah, definitely it's a major challenge, but we're working on it and we're doing a pretty good job. We do have that deployment right now in downtown Toronto on Yonge Street. It's a work in progress and we're doing pretty good so far.
Someone asked, how do you estimate travel time from point A to Z? Do you just sum up all intermediate segment travel times, A to B, B to C, Y to Z? And they also asked, is travel times weighted with volumes detected?
So I'll take that one. So absolutely, it's A to B plus B to C plus C to D, etc. So from sensor to sensor, we create the links and do our best to calculate the travel time between those links and then add them up for the overall route. And the second question was, regarding volume, absolutely not. We don't, although we take into account the quality of the data based on whether or not we have enough samples to estimate the travel time, that's our only nod towards volume. We don't, we actually don't know how many vehicles are actually going through that area.
Someone asked, for the origin destination survey, how long in hours would be sufficient to get a good sample size?
It's a little bit outside of my expertise, Michael. Any thoughts?
No, me as well. To be honest, this has not been done nearly as much as I would like it to be done. And we've had people approach us in the past to say, we want to do, as part of a transportation master plan, we want to survey it for a week or something like that. And have asked, is that sufficient? And really it comes down to volume of traffic. And there's no, as far as I know, specific planning guidance or kind of information on exactly how many days of collection equal this much volume on the roadway. So I don't have a good answer on that, unfortunately.
The answer depends on the it depends on the answer. So you know, within this area, if there's 5 million people traveling between A to B, then you know, you could be done within a few minutes. But if you've got you know, only 5 people, you're going to have that sensor out there for weeks on end. So it depends on the volumes, and ultimately the best way is you put it out there and you collect the data. But if you have volume data, then I'd probably be able to provide you with a bit of a better estimate based on experience with having done this before. But it really depends on the volumes. Yeah.
Yeah, and just the final thing, that's totally accurate. And what I've constantly run into is people wanting to do just a few days. And what I often encourage is that the cost to deploy is the vast majority of the cost associated with getting a sensor out there. So if you're going to deploy and remove it anyways, whether it's 3 days or 3 weeks, aim for a week or 2 at least, because it doesn't cost you anything beyond a little bit of data on the SIM card to kind of keep running it. So yeah, I would just aim for longer than shorter, because the cost differential is very little, and you'll have a lot more data to work with.
In Calgary, we did roughly a month or so for decent OD data. Yeah,
that's useful.
Yeah.
Someone asked, does MTO provide those MAC addresses? We are looking to do an area origin destination survey, and having the data on 400 would help connect with the data we would collect within the rest of the city.
I would say that yeah, if you were to approach MTO, you'd be able to get that that answer. The data ultimately resides with them. I will also mention, just because you know, it is I think that leads to the next question, which is, are we violating privacy for providing MAC addresses? And I will say that all of these MAC addresses are encrypted, so even I would not be able to track any person on this grid. And so I'm going to answer by saying I would feel comfortable if MTO shared those MAC addresses for you know, purposes of research, etc.
Yeah, and just to be clear, though, they're not the raw MAC addresses themselves.
Yes.
They're hashed and encrypted at the edge, so you would have kind of the result of that encryptment. But as long as you have kind of the encryptment method and the keys associated with the hash key, you could kind of get back to the source. So that's typically what we would see, and we have seen people request that in the past, but not so frequently. But certainly a question for the MTO and their discretion.
Mm-hmm.
And that looks like the end of the questions.
Beautiful. I thought we were going to go way over. So with that, thank you everyone for taking the time today. Like Sam said, we'll send out the slides and the recording tomorrow. And I do want to give a big shout out to Black & McDonald. They've been a great partner throughout this project, and we couldn't have done it without them. So thanks to them, and Yates, thank you so much for taking the time today. It's been a pleasure.
Thank you.
All right, take care everyone. Bye-bye.